like to present a conference paper which is titled about model-based hierarchical clustering for categorical data. As an research assistant and a graduate student from Concordia University under supervision of Professor Nizar Boukila. So for this presentation.
Excuse me, would you please use the full screen mode while presenting?
Like this?
More.
Sure.
بس حطيها على الباوربوينت برزنتيشن.
لأنها PDF.
PDF. اوكي ما عندك مشكلة. كويس كده. شكرا كده كويس.
We are going to introduce some important concepts regarding our proposed model and some limitation regarding the existing approach and how we can overcome this limitation. And we validate the proposed model by 2 real-world applications and we show the results. And finally, we will conclude the presentation and we will have time for questions. So for the importance of data analysis, because of each day there is a huge amount of data that is generated and need to be analyzed to extract hidden knowledge and get benefit from this data which is generated every day and from different perspective and from different technique. And it's better to have like innovations and automatic technique that it can learn from itself. So from this point of view, we have like clustering task as unsupervised learning approach is a widely used and efficient to group data points into homogeneous group, for example, clusters. And there is different type of data, like discrete data or binary data. And for each type of data, the clustering for it is applicable for different applications. For example, in discrete data, the clustering of discrete data is applicable for data mining, machine learning, image processing, and computer vision applications. While in binary data has similar applications, but there's places where binary variables are used rather than continuous or discrete variables. So each data type has its use. So clustering this kind of data type and understanding the structure of this kind of data will get more benefits from this data when we clustering appropriately using appropriate model and appropriate technique to this specific type of data. So for hierarchical clustering, we have 2 approaches. Hierarchical clustering, simply to make it simple to understand, is like a tree. It has a root and leaf. So it has 2 approaches. It has top-down approach and bottom-up approach. For top-down approach, we are going from root to leaf, and to specify more in this term, all the data points will be in one singular cluster, and then we are partitioning this singular cluster into more than one cluster until we reach to the point of each data point will have it as a cluster. While the bottom-up approach will be opposite of top-down, where we are treating from the beginning each data point as a separate cluster. Then we calculate the distance between this singular cluster, which has data point, just one data point, with other, and find the closest one. Then we are merge this level of a cluster until we reach out to the hierarchical level, top of the hierarchical level. And this picture is explain more the difference. The top down is from top to down, and bottom to up is from bottom to up. So the hierarchical clustering algorithm is actually traditional hierarchical clustering algorithm, and when we when we consider the finite mixture model with hierarchical clustering algorithm, we are talking about a probabilistic distance between the components, where the component is considered as a component of finite mixture model. So each cluster is a component of finite mixture model. Is not just one data point, like we said in the previous slide. Now we are talking deep when we specify hierarchical clustering algorithm with finite mixture model. So, for example, we have A and B is considered as 2 points. 2 data points are in the class C, and we have E and D, 2 data points are in class F. Class F and class C consider as a component of finite mixture model. So we wanted to compute the probabilistic distance between F and C, F and C, and to find the closest distance to merge them together. So C has A and B and bigger cluster, and so on. We continue like we have until we reach out to big cluster, which is the root, which has subclusters inside. This is the hierarchical cluster algorithm. However, this hierarchical cluster algorithm has some limitations. First of all, if the data points are near the center or the mean, it cannot be clustered properly. So this is one of the disadvantage of this traditional hierarchical clustering. And also hierarchical clustering cannot propose or cannot give or provide any guidance regarding the correct number of classes to burn the tree. And also the traditional hierarchical clustering use Euclidean distance to measure the distance between data points. And Euclidean distance sometimes is not suitable for all the data type, especially for structured data such as images. So that's why bottom-up approach need to be improved to overcome one of these limitations or some of them. And then our contribution is to propose agglomerative algorithm, which is bottom-up hierarchical clustering based on multinomial for the discrete data to get the benefit of discrete data. And also we propose the agglomerative algorithm based on Bernoulli mixture model for binary data to get benefit of the application of binary data. So the distance between the cluster should be changed, not Euclidean distance. We need to use Bhattacharya and callback instead of using Euclidean distance to get better results. And we validate our proposed framework by applying two real-world application, which is text document clustering and image categorization. The proposed model is basically we consider two important points, then which is using the distance Bhattacharya and callback, considering applying multinomial and Bernoulli distribution to compute the similarity or the distance between multinomial distribution and Bernoulli distributions, and we calculate the accuracy, which is average based on confusion matrix to validate the cluster. So here we have the distances that are based on multinomial distributions, the Bhattacharya distance and callback distance to get the probabilistic distance from two multinomial distribution. And these are the two distances, which is the same Bhattacharya distance callback, but with considering Bernoulli mixture model. For this equation, we are explaining the joint probability of finite mixture model. In case of multinomial, we need to use the probability distance function, which is related to multinomial. In case of Bernoulli, we need to change this and use the appropriate Bernoulli distance function. probability distance function to make the suitable, to use the suitable equation for each model. So let's consider this as a data set which has from 1 to n. For example, let's say we have 100 images or 200 images, so the data set will be from 1 to 200. Then each data point, which could be document or could be image, consider as a vector, a d-dimensional vector, and for the parameter for multinomial distribution, we have the suitable parameter regarding the multinomial distribution, and Bernoulli distribution has its parameter. And regarding the weight, it should satisfy its condition, which is any number from 0 to 1, and the sum of the weights should be equal to 1. We have applied also the expectation maximization approach to estimate the parameters and to train the mixture model. So expectation maximization approach is actually based on 2 steps, which is E step. E step is expectation. We calculate the posterior in this step, and the maximization step we update the parameter and we continuous and iteratively doing these steps until we reach to covariance level. Okay, this is the expectation step. We calculate the posterior probability for each data point, and we count the maximum, and we consider the maximum posterior and assign the data point to the class that correspond to the maximum posterior. And then we update the parameter in the maximization step. And then the expectation and maximization step are iteratively processed until covariance. So this is the complete learning algorithm. From the beginning, we initialize all the parameter. In the E step, we compute the posterior probability, and in the M step, we update the parameter. And then we assign the data point to the cluster based on maximum posterior probability. So from step 1 to step 5, we are applying mixture Bernoulli, mixture model. If it is multinomial, it will be multinomial mixture model based on equation 2 when we change equation 2 to multinomial. And if we wanted to apply the Bernoulli, we change also the equation 2 to Bernoulli. And we apply from 1 to the step 5 Bernoulli mixture model or multinomial mixture model. Also, we register or we save this accuracy or the result to compare it with Heirachical. So from 6 to the end, we are applying the Heirachical clustering. So in the 6th step, now we try to calculate the probability distance between each cluster after step 5, and try to find the minimum distance to find the closest cluster to merge the clusters together. And when we find the minimum distance and merge them, then we update the label, because when we are going up, we are merging a cluster, so the number of clusters are reduced. So we need to update the label and reduce one cluster that is merged, and until we reach the top of Heirachical cluster. For experiment results, we calculate the average accuracy based on confusion matrix to see the performance of our proposed algorithm. So here we test three text data sets. And for these three text data sets, we have applied three things to compare regarding the multinomial, and also we have applied also three things in Bernoulli. So for multinomial, for this column, we have applied the multinomial mixture model, uh, which is from step 1 to step 5. And we save the result as we said, which is for 7 sector, it is 49. For WebKP4 is 86, and for NEBS is 79, is around this number because of the decimal. So these are the accuracy when we applying the multinomial mixture model. And when we apply the hierarchical based on callback distance, we have this result, which is improved from 49 to 70, 86 to around 96, and from 79 to 90. And the same thing happened when we apply the beta sharia and we compare it with multinomial mixture model. We see the improvement and when we apply these three data sets, which is text data sets. And for Bernoulli also we have applied the same. We testing the Bernoulli mixture model for these three text data set. It starts from 73 here for 7 sectors and 90 for WebKP4, and for NEBS is 82. And when we apply the hierarchical clustering using callback and beta sharia, we have increased it to 97, around 97, while here in beta sharia for NIBS is a little bit less, which is 94, but still is improvement from 82 to 94. It's improved in accuracy. And this is an example of one of our text dataset, which is 7 sector text dataset. This is how when we draw it, how the cluster happened, our hierarchical cluster happened. It is start the healthcare. We calculate the distance between healthcare and every cluster, and we found that the technology is the nearest one or the closest one, so we merge them, and so on. We complete until we reach to the hierarchical level. And here is the hierarchical clustering result, but for two image datasets, which is KTH and SUN. KTH is texture image, while SUN is color image. We apply the same. In the multinomial, we apply the multinomial mixture model, and we find this is the result, 78, around 78. And it is improved from 78 to around 97 in callback and beta sharia, while in this using SUN dataset, the accuracy is not really high, is 29 by applying the multinomial, but by applying our hierarchical proposed hierarchical framework, we increase it significantly from 29 to 82, and based on callback, and 67 based on beta sharia. And for Bernoulli, we see similar thing because SUN is still considering Bernoulli mixture model doesn't give us high accuracy, but with our proposed framework is give us higher or higher performance in this application. And this is example of the KTH dataset, which is image dataset based on Bernoulli distribution. We can see that aluminum foil and brown bread are closest, then it merged together, then they count the similarity that the closest one will be the cotton, and sometimes other level of hierarchical, like here, cracker and sponge are merged first and then merge with other level of hierarchy. So it's depend about the experiment and depend on the data itself how it will be clustered, and the distance, what is the closest. So it's not this. It's not all the time. It will be the same. This hierarchy. It can be like this picture. And to conclude our contribution or this presentation, we can say that we have a proposed hierarchical clustering approach based on multinomial and mixture models, considering using Bhattacharya and callback distance for categorical data. And the performance show that it can be efficiently used to measure similarity between two discrete distributions. And the proposed approach can be applied in future for in any application or other application which involve hierarchical structure for count or binary data. Thank you so much, and it's time for your questions.
Thank you for the nice presentation.
You're welcome.
Thank you very much for this scientific paper that you shared with us here. Any question, please? The floor is open for Q&A. Any question, please? I think there is no question. However, I'm going to ask you a simple one.
Okay.
When it comes to modeling, there are different types, at least three different types of model.
Yes.
An AMI model, statistical model, and logical model.
Yes.
How would you classify the hierarchical model that you have developed, under which category and why?
Sorry, but can you repeat your question? Sorry about that.
Well, normally when it comes to modeling, there are three basic models: statistical model, AI model, logical model. And my question is, which category your hierarchical model falls into and why?
Yes, statistical, because we are based. This proposed work is based on Bernoulli and multinomial mixture model, which has considered the probability and statistical computation, and also the parameters when we updating them or calculating them. We consider a lot of aspects of statistical approaches or statistical calculation.
Thank you very much for your input and for your answers. Thank you.
Thank you for having me in this great conference and giving me a chance to present my work in this great conference. I really appreciate it, and it is a really great conference. Thank you so much for all your hard work, and I appreciate it. Really appreciate it.
Thank you.